And we're back. After the last presentation had so many hiccups, I actually took some time off and I tried to proofread these slides rather carefully. I hope I've been able to do that. We'll be talking about the residue theorem now, which is one of the, well, central theorems of complex analysis, if you will, from the point of view that the residue theorem allows a lot of computations that otherwise would not be possible. Let's take a look at it. Basically, what we know is that the Cauchy-Goursat theorem tells us that if a function is analytic on and in a closed contour, then the integral over the closed contour is 0. So one way to look at the residue theorem is that we want to find out what happens if the function is not analytic. Well, there are two possibilities in which this could happen. On one hand, the function could blow up on the contour, and that we will actually avoid. Which means that we will not need to generalize contour integrals to things like improper contour integrals, and that's really good too. But the situation in which the function is not analytic inside the contour, that turns out to be very interesting. That is the domain of the residue theorem and the calculus of residues that follows it. Now, what we will do in this presentation is we will prove the requisite theorem, which is the residue theorem. And we will also lay some abstract groundwork talking about singularities and then types of singularities and how to find certain kinds of residues. And we will then spend quite a bit of time with examples that show how widely applicable the residue theorem is, and that will actually not just be this presentation, but also the next one on the calculus of residues, which will have a lot of neat computations of integrals. Okay, so let's start out with the singularities. Let's take a look at the function f of z equals 1 over z minus 1 over 1 plus z squared. That function is not analytic wherever the denominator is 0, and that would be at z equals 1, because that's where z minus 1 is not defined, and then at z equals plus minus I, because that's where 1 plus z squared is equal to 0. Okay, so in the realm of the residue theorem, we will always want to just draw the complex plane and then we'll give ourselves a scale and then visualize that the singularities are at 1, at I, and at minus I for this one. And well, if we take a look at a different function, f of z equals 1 over sine pi over z, that function is not analytic wherever the denominator is 0, which would be because the sine function is 0 at integer multiples of pi. That would be at z equals 1, 2, 1, 1/2, 1/3, 1/4, because that'll give us pi, 2 pi, 3 pi, 4 pi, and at 0, and also at the negatives of these values. Yeah, and I said and at the negatives of these values, and if we want to picture that, we look at our complex plane again, and we get this singularity at 1, at 1/2, at 1/3, all the way down to 0, and from the left at -1, at -1/2, -1/3, also converging to 0, if you will. Okay, so the definition that is underlying these ideas is that if a function is analytic for 0 strictly smaller than z minus z0 strictly smaller than r, then z0 is called an isolated singularity of f. Now, the function may still be analytic at z0. We'll talk about what kinds of isolated singularities we have later on, but right now we're just going to assume, and that's typically the assumption, that something goes wrong at z0. So for example, z equals 1, I, and minus I are isolated singularities of the first function that we talked about, 1 over z minus 1, 1 plus z squared, and the z equals 1, 1/2, 1/3, 1/4, those are isolated singularities of that second function, 1 over sine pi over z. So are the negative values, of course, but 0 is not an isolated singularity of 1 over sine pi over z, and that's because at 0 we've got a bunch of singularities piling up, which means that we will not be able to find the deleted neighborhood of 0 inside which 1 over sine pi over z is analytic. 0 is not an isolated singularity of the logarithm function or of any root function. That sounds very tempting that it should be, but remember that every branch cut of the logarithm, and therefore of the root function, must contain the origin, and that means that these functions will not be analytic on a deleted neighborhood of 0, because that branch cut will always take the annulus or the punctured disk and actually cut it open. Okay. Now, if the function is analytic for 0 strictly smaller z minus c0 strictly smaller r, then it certainly has a Laurent expansion about z0, and the coefficient c negative 1 is called the residue of f at that singularity z0, and it's also denoted residue at z equals z0 of f, and we just denote that thing, denote c1 to be just that expression. And we will see the relevance of the residues in the next result. So let's see. If our function is analytic for 0 strictly smaller z minus c0 strictly smaller r, and if c is a positively oriented simple closed contour around z0 that is contained in this punctured disk, then the integral over the contour of f of z dz is 2 pi I times the residue at z equals z0 of f. And the proof, well, from the theorem on the Laurent expansions, we have that the residue is a minus 1 if we're using those positive and negative, or if we're using those double-sided coefficients, and a minus 1 from that theorem is 1 over 2 pi I integral over c f of c divided by c minus c0 to the negative 1 plus 1, and then of course the denominator goes away, so this is 1 over 2 pi I integral f of c dx, just like we claimed it to be. And remember, the little circle just means that we're integrating over a closed contour. And so here c is any circle around z0 with radius smaller than r. That's what we did prove in the theorem on the Laurent expansions. Now we want to replace the circle with any contour around the origin, and that requires an argument that is similar to the one that shows that we can use circles of any radius. Namely, we take our arbitrary contour, which is supposed to be positively oriented, we pitch it against a circle that is negatively oriented, and well, if the center is z0 or 0, it doesn't really matter that much. And then we just cut them open and connect them in such a way that we get a completely positively oriented contour. And now there is no singularity of the function inside this big contour, which means the total integral is 0. This integral cancels against the other integral along those straight line segments as we let these points go towards each other, and that means that the positively oriented integral over c plus the negatively oriented integral around the circle, that's equal to 0, and that means that the integral over the contour is equal to the integral over the circle when both are positively oriented. Okay, let's take a look at some examples. We take the unit circle traversed in the positive orientation, or in the positive direction. Then the integral over the unit circle of e to the z divided by z dz, that's 2 pi I. And that's because the function e to the z over z has only the singularity at the origin inside the contour. And the residue, if we're expanding e to the z over z, is 1 over z plus sum n equals 0 to infinity z to the n over n plus 1 factorial. That's just the power series expansion of e to the z divided by z. And that means that the residue, which is the coefficient of the 1 over z, is 1. And that means if we apply the preceding theorem, we get that the integral has got to be 2 pi I. The direct computation, notice, would give us the same result, because the integral of this power series part over any closed contour is 0, and the integral of 1 over z dz over the closed unit circle is the integral from 0 to 2 pi 1 over e to the I pi I e to the I 1 over e to the I theta I e to the I theta, and that's just 2 pi I after canceling the e to the I thetas. If we're staying with the unit circle traversed in the positive direction, then we claim that the integral of e to the z squared over z squared dz, that's equal to 0. And that's because the function e to the z squared over z squared also only has the singularity at the origin inside the contour. But the residue of e to the z squared over z squared, if we expand that, it's the same thing as what we had on the previous panel, except that the z's are replaced with z squared, so we get 1 over z squared plus sum n equals 0 to infinity z to the 2n over n plus 1 factorial. At z equals 0, that residue is 0 because we don't have a 1 over z term, and that means a minus 1 is equal to 0. Again, we apply the preceding theorem. Okay, so the residue theorem now puts that together in a context when we've got more singularities. So we take a simple closed positively oriented contour, we let z1 through zn be inside the contour, and we let f be analytic on the contour and in its exterior, except possibly at the zj's. Well, then the integral, or 1 over 2 pi I integral f of xi dxi, is equal to the sum of, for j equals 1 to n, of the residue z equals zj of f. So the proof is, if we have that Cj is a positively oriented circle around Zj, so that no two of these circles intersect, and so that they're all contained in the interior of C, then by our extension of the Cauchy-Goursat theorem that we already had proved, we have that the integral of f of z dz is the sum j equals 1 to n integral over the Cj's f of z dz. And now these circles contain one singularity each, so we can use what we had just proved and show that this is 2 pi I sum j equals 1 to n residue z equals zj of f. And that is the proof because, well, we could still divide by the 2 pi I here, but that, of course, is rather trivial. Okay, examples for using the residue theorem. If we're going to integrate the function f of z equals z squared over z squared plus 1 over the positively oriented boundary of the square of the numbers z equals x plus iy, where xy is in the square negative 3, 3 cross negative 3, 3. Well, let's first take a look at what that looks like. We get a square that is traversed in the positive direction, and the radius, if you will, of the square is 3. Well, now we need to find the singularities, and z squared plus 1 has zeros at I and at minus I, and so that means we need to find the residue at I. Well, z squared over z squared plus 1 is z squared plus 1 minus 1 over z squared plus 1, which is 1 minus 1 over z squared plus 1, which is 1 minus 1 over z plus I over times 1 over z minus I. And so the coefficient of 1 over z minus I ought to be the value of this function at I, and that is something that we'll ultimately also formally prove with our theorem on residues at poles, but it does make sense because this thing is continuous, so this will have a power series expansion, and so its value at I will be what the coefficient of 1 over z minus I will be. And so the residue at z equals I of z squared over z squared plus 1 is negative 1 over I plus I, which is negative 1 over 2I. And remember, 1 over I is negative I, so this means this is actually I over 2. The residue at negative I, well, z squared over z squared plus 1 expands in the same way. It's still 1 minus 1 over z minus I, 1 over z plus I. The only thing that I changed is the order of the factors at the end. And so this time the residue ought to be the value of 1 over z minus I at negative I. So the residue at z equals negative I of z squared over z squared plus 1 is negative 1 over negative I minus I, which is 1 over 2I, and 1 over I is negative I, so negative I over 2 would be the answer here. So see that sometimes you actually use the same computation to get the residues at two different places. Sometimes if it doesn't factor this nicely, if it doesn't break apart this nicely, you actually will have to do some different kind of algebra, or ultimately use theorems such as the one that we'll prove at the end of this presentation. Okay, well, that means now that the integral of z squared over z squared plus 1 over this contour C is 2 pi I times the sum of the residue at I and the residue at minus I. which is 2 pi I times I halves plus negative I halves, and of course that is 0. Okay, the residue at infinity is something that can help when you've got a bunch of singularities inside a contour and none on the outside. And well, here's how it's defined. If f is analytic on the complex plane except for a finite number of singular points z1 through zn, and if we assume that R1 is so that all the zj's are in absolute value smaller or equal than R1, then for any R0 that is greater than R1, we let C0 minus be the circle around the origin of radius R0 that is traversed clockwise, that is in the mathematically negative direction. Then we define the residue at infinity of f as residue at z equals infinity of f being 1 over 2 pi I integral C0 minus f of z dz. Well, and you will rightly say, what does that have anything to do with an integral around a contour that contains everything? Or how does that help? Let's just say, how does that help? Because after all, this would be the integral that we're interested in, or actually we would be interested in its negative, because we're usually interested in positively oriented contours. Well, let's take a look. The residue at infinity is 1 over 2 pi I integral C0 minus f of z dz, which is a negative 1 over 2 pi I integral C0 plus, which would now denote the integral over the positively oriented contour, f of z dz. And now remember that even though we are taking a whole disk out of the domain, out of the complex numbers, the Laurent expansion works on any domain that is shaped like an annulus. In particular, it works on the complex numbers if we remove a whole disk. So that means this function still has a Laurent expansion, sum n equals 0, n equals negative infinity to infinity, cn z to the n around the origin. And we know that that integral just ends up being negative c negative 1. And we know that that is equal to, and here's where some acrobatics come in, this is negative 1 over 2 pi I integral c0 plus sum n equals negative infinity to infinity cn minus 2 over z to the n. And that is, well, why is that right now? Because now we would get, oh yeah, this one only gives us a non-zero integral when n is equal to 1, and when n is equal to 1, the integral gives us 2 pi I c negative c1 minus 2, and that's c negative 1. Okay, so that looks like a cheap trick to get power series involved that use 1 over z to the n, and in fact that's exactly what it is. Now we factor out a 1 over z squared from this power series to get something that actually looks like the expansion of the function f. We still have the cn's, it's just shifted. And so this means this is just negative 1 over 2 pi I integral c0 plus 1 over z squared f of 1 over z dz, which is an integral of a rather strangely defined function, but at the same time what we get is we would only need to find the residue of this strangely defined function at 0 in order to get the integral of f of z dz over the positively oriented contour. So, and that is the negative of the residue of this function at 0. Okay, so that means if the function f is analytic except for a finite number of singular points that lie in the interior of this positively oriented simple closed contour C, then the integral over C of f of z dz is 2 pi I times the residue z equals 0 of 1 over z squared f of 1 over z, and the proof was just given on the previous panel. The advantage of this theorem is that we only have to compute one residue, namely the residue at 0 of this strange function, which we then also define to be the residue at infinity of the original function with some negative signs thrown in. And I guess we'd have to be really careful. This contour could dip inside the circle that contains the singularities, but that's not a problem because we would just do another one of those arguments that shows that if we have any two contours between which there are no singularities, then the integrals are the same. Alright, so if we were to use this theorem to integrate f of z equals z squared over z squared plus 1 over the boundary of the square negative 3, 3 cross negative 3, 3, well, we would again just have this set up as we had before with the I and the minus I. And this time, however, we would look at the function 1 over z squared f of 1 over z. And that's 1 over z squared, 1 over z quantity squared divided by 1 over z quantity squared plus 1. Multiplying with z squared on the bottom gives us 1 over 1 plus z squared, and the 1 over z squared comes down from the top, or yeah, there's a variety of ways to do the algebra, but that's what we get. Yeah, and so that is 1 over z squared, 1 over 1 minus negative z squared. Now we're just trying to get an expansion. That's 1 over z squared, sum n equals 0 to infinity, negative 1 to the n, z to the 2n, just using the formula for the geometric series. And if we now break that up, well, then that is that the term n equals 0 gives us a constant, so we get 1 over z squared here, and then from n equals 1 on we have powers z to the 2n minus 2, which are all positive, and that means that the integral, which is 2 pi I times the residue at 0 of this function, is actually equal to 0 because that residue is equal to 0. Okay, now let's take a complex number, z0, let r greater than 0, and let f be analytic in a deleted neighborhood of z0. Well, in this case, z0 is called an isolated singularity of f. And we're now going to consider the Laurent expansion of f around z0, which has this power series part, a n z minus z0 to the n equals 0 to infinity. And then it also has this power series with negative powers, b1 over z minus z0, b2 over z minus z0 squared, b3 over z minus z0 cubed, and so on. And the sum of those negative powers of z minus z0, that's the principal part of f. That's also what that's called. And if bn is equal to 0 for all n, then z0 is called a removable singularity. That should be pretty clear because f is in that fashion. If all those b's were 0, then f is just a power series around z0. And so that means we can just throw the singularity away and define the function at that point. If there is a positive number m so that bm is not equal to 0, and bn is equal to 0 for all n greater than m, then z is called a pole of order m. So that would mean we have, say, it goes up to b3, and after that there is nothing. That means we've got a z minus z, the division by 0 minus z0, we've got a division by z minus z0 squared, we've got a division by z minus z0 cubed, and that's it. And those things were called poles on the real line, and so why shouldn't we call them poles in the complex plane too? And if the number in this second part equals 1, then z0 is also called a simple pole. Those things have a special position because they arise surprisingly often, but also because a simple pole then very quickly can give you the residue, and we've got a very short Laurent expansion, of course. And if z0 is not removable and there is no number as in part 2, which means we've got infinitely many b sub m's that are not equal to 0, then z0 is called an essential singularity. And those things are rather nasty, and for the most part we'll stay away from them, even though the residue theorem, of course, still applies to them. So, examples. Well, sine z over z has a removable singularity at z equals 0, and that's because sine z over z is 1 over z sine z, which is 1 over z times the power series expansion of the sine function, negative 1 to the n over 2n plus 1 factorial z to the 2n plus 1, which is the sum n equals 0 to infinity, negative 1 to the n, 2n quantity, 2n plus 1 quantity factorial z to the 2n, which is a power series. The function f of z equals 1 over z, 1 minus z squared has simple poles at 1 and at minus 1, and that's because 1 over 1 minus z squared is 1 over z plus 1, 1 over z minus 1. As I mentioned, we'd actually have to show that there are no higher powers. We will do that ultimately in this theorem on residues at poles, but it does seem to make sense that this ought to work out. The function 1 plus z squared over z cubed has a pole of order 3 at z equals 0. 1 plus z squared over z cubed is of course 1 over z cubed plus 1 over z. So here we have the Laurent expansion, and the pole really is of order 3. And the function f of z equals e to the 1 over z has an essential singularity at z equals 0. That's because e to the 1 over z is the sum n equals 0 to infinity, 1 over n factorial 1 over z to the n. And we can see that these coefficients b sub n, actually all of them are non-zero. And that means that's about as essential a singularity as you can get. Okay, our final theorem is about the computation of residues. So we take this function f that is analytic in the deleted neighborhood of the point z0. Then z0 is a pole of order m if and only if there is a function phi that is analytic in the neighborhood of z0, so that phi of z0 is not equal to 0, and so that f of z is phi of z over z minus z0 to the m for all f in a deleted neighborhood of z, for all z in a deleted neighborhood of z0. That is something that we implicitly already used in a couple of those examples. It seems to make sense, and the proof is not going to be too bad. The nice thing is we will also get that the residue of f at z equals z0 is the m minus first derivative of phi at z0 divided by m minus 1 factorial. Okay, how do we prove that? Well, if the function has a pole of order m around z0, or at z0, I guess, then the Laurent expansion for 0 smaller z minus z0 smaller r for some radius is, with our c minus m not equal 0, just the sum n equals negative m to infinity cn z minus z0 to the n. Remember, the negative coefficients for indices smaller than negative m, those will all be 0, so we can start our sum at negative m. Well, that means we can pull out a 1 over z minus z0 to the m and get a sum n equals negative m to infinity cn z minus z0 to the n plus m. Then we do an index shift, k equals n plus m, which means that the exponent becomes k. If k equals n plus m, then n equals k minus m. That works out too. When k equals n plus m, n equals negative m, k equals 0, n goes to infinity, k goes to infinity. That works out. So that means that this sum becomes this sum, and the 1 over z minus z0 to the m, of course, we just kept. And now this thing here is an analytic function, so that is our phi of z divided by z minus z0 to the m. Conversely, if our function is phi of z over z minus z0 to the m with phi of z0 not equal 0, then the above computation in reverse shows that f has a pole of order m at z0. And that's because, well, we just take that, we realize that phi has a power series expansion, which we can write down any weird way we want, including calling the coefficient ck minus m, and then we undo the index shift and get all the way back to this function f of z. Okay. Moreover, in this situation, remember the coefficient c negative 1, which is the residue of f at z minus z0 of the Laurent expansion of f, is the coefficient am minus 1 of the power series expansion of phi, because what do we have? Our c negative m is the 0th coefficient of the power series expansion of phi, and c negative m plus 1 is the first coefficient of the power series expansion of phi. No, wait. There's something that I'm not seeing right here. Oh yeah, sure. C negative m plus 1 really is the first coefficient, and you just keep going like that. What you want to have is c negative 1. That's where k would need to be able to m minus 1. And the coefficient in the power series of the power m minus 1 is actually the coefficient am minus 1, and the coefficient am minus 1 of capital phi is the m minus first derivative of phi at the point of expansion divided by m minus 1 factorial. Alright, that is just one of those where you just have to really deal with the index shift. But it wasn't that bad, and well, now let's see how this one works. Find all the poles, their order, and their residues for the function z plus 1 over z minus 1 cubed. Well, the only singularity is z equals 1. And f of z is z plus 1 cubed over z minus 1 cubed, which is written as 1 over, can be written as 1 over z minus 1 cubed, and then z plus 1 cubed expanded to z cubed plus 3z squared plus 3z plus 1. That means that phi is z cubed plus 3z squared plus 3z plus 1, and m is equal to 3. So we need to find the derivative, which is 3z squared plus 6z plus 3, and the second derivative, which is 6z plus 6. Now the second derivative of phi at 1 is not 12. The second derivative of phi at 1 is 6. No, I must be getting tired. The second derivative of phi at 1 is 12, because 6 plus 6 is 12. Come on, I can do this. I've done this for a while now. Okay, so the residue at z equals 1 of f is therefore then 12 over 2 factorial, 3 minus 1 factorial, 12 over 2. That's the 6 that we're getting back here. Okay, next example, show that the residue at z equals I of principal branch of the logarithm of z divided by z squared plus 1 squared is pi plus 2i over 8. So these computations don't need to work out pretty. The main thing is that they do work out. So the logarithm over z squared plus 1 quantity squared is the logarithm over z plus I times z minus I quantity squared, which is 1 over z minus I squared logarithm of z divided by z plus I squared. So again, we just factor out 1 over z minus where we want to take the residue. Phi is the principal branch of the logarithm divided by z plus I quantity squared. M is equal to 2, which means we need the first derivative of phi. Well, that's a quotient rule. Derivative of the numerator 1 over z times denominator z plus I quantity squared minus derivative of the denominator 2z plus I times 1, if you will, times the numerator log z divided by denominator squared, so z plus I taken to the fourth. Now we cancel a z plus I, which we can because it occurs in both factors in the numerator. So 1 over z plus I minus 2 log z divided by z plus I cubed. And I think now I just push the 1 over z in the denominator, right? So we get, if we multiply numerator and denominator by z, we get z plus I minus 2 log z times c divided by z times z plus I cubed. Phi prime at I would be I plus I minus 2 log I times I divided by I times I plus I cubed. That gives us 2I minus 2, and remember I is e to the I pi over 2, so the log of I is I pi over 2 times the I from the back, from the z in the back, and then here I times 2I cubed, that's all we have. And if we now work that out, we keep the 2I, I times I is negative 1, so the minus turns into a plus, and the 2 pi halves, of course, is a pi, so we get plus pi. In the denominator, we've got I times I cubed, which is I to the fourth, which is 1, and 2 cubed is 8, so that one works out. And there it is now. Well, we have to divide by 1 factorial to get the residue, but that just doesn't do anything, of course. Finally, let's get a first taste of what the calculus of residues will do for us. We want to integrate the function f of z equals 1 over z cubed z plus 4 around the positively oriented circle of radius 5 around the origin. And we will need the residues of f at 0 and at negative 4 because both singularities are inside that circle, both singularities which are 0 and 4. And the same way we could also, because all the singularities are inside the circle of radius 5, we could use the residue at 0 of 1 over z squared f of 1 over z, and I think that's what we'll do. 1 over z squared f of 1 over z is 1 over z squared 1 over z quantity cubed times 1 over z plus 4, and 1 over the z squared times the 1 over z cubed in the denominator here, that turns into a 1 over z. In the other part, I just found the common denominator, which is 1 plus 4z divided by z, and so that gives us z squared over 1 plus 4z. And that one doesn't have a singularity at 0, and that means the integral, which would be the residue of this function at z equals 0, that integral must be 0. And that's it. Okay, well, we had fewer hiccups than the other one. That's good. I will strive to eliminate the last few also. The next presentation will be, if I remember correctly, on the calculus of residues. Let me double check that real quick. No, we'll first talk a little bit about how zeros and poles are related, and then we will do a lengthy presentation on the calculus of residues, which will allow us to solve all sorts of integrals that, as long as we only have real analysis available, we would not want to touch with a 10-foot pole. All right, I'll see you there. Thanks a lot.